All right, so another example from 5.3, conditional probabilities, tree diagrams, stuff like that, multiplication rule. Example, false positives and HIV testing. Percentages are fictional. Yeah, I kind of just made them up, but I guess they could be perhaps close to actual values. Who knows, right? Suppose 1% of the population is infected with HIV. Oh, actually, no. Let me go on record here. This is absolutely made up because I did not research HIV. Nor do I know what percentage of any population is infected with HIV. So I did just make this up. The probability of a false negative, is 3%, and the probability of a false positive is 6%. So false negative. So that's whenever you test for HIV and the test comes back negative. However, it's a mistake. So it comes back negative, but you really do have HIV, unfortunately. A false positive would be a test that comes back positive, so it tells you that you have HIV, but that's a mistake. So that's not quite as bad. You're going to kind of freak out thinking you have HIV, but eventually you'll figure out and get tested again and figure out that you don't actually have it. So I guess you could kind of talk about which one of these is actually a more serious mistake. And I think you should conclude that a false negative is worse, because a false negative would be somebody that goes to get tested. They're responsible, and the hospital tells them that they don't have HIV, so they go out and they don't know they have it. So they could spread it to other people. Whereas this one, although it's scary, eventually you will figure out that you don't have it. Regardless, suppose a person tests positive for HIV. Find the probability that this person actually has HIV. So if you test positive for HIV, so this is the probability, find the probability that this person actually, so find the probability you have HIV. I would just call that HIV, given you test positive. So when I do this in class, I ask the kids to kind of estimate what percentage you think this is. I mean, if you test positive for HIV and there's a 3% false negative and a 6% false positive, what's the probability you actually have HIV? And you can do that now if you're watching the video. Throw out a guess. A lot of people will throw out some pretty high percentages. They might actually throw out a 96 or a 97. I don't think it's either one of those. Well, I know it's not either one of those, but they usually guess pretty high, like maybe 80% or maybe 90%. I think you're going to be surprised by the answer. So let's find out here. So first of all, let's write down these things that we're given. First of all, this is the probability that you have HIV in the population, or probability a randomly selected person would have HIV. This is the probability that you test negative and it's a mistake. So this is a probability that you test negative given. So if it's a mistake and you test negative, that means you really do have HIV. So this is a conditional probability. This is a probability that you test negative given you have HIV. That happens 3% of the time. If you have HIV, you should test positive, but you're not. And then this is a probability that you test positive given. So if you test positive and it's a mistake, that means you don't actually have HIV. So you have no HIV. And that's 0.06. So those are both mistakes. All right. So again, I don't know if you realize this, but we're reversing the conditions. I'm giving you information about these conditional probabilities, and I want you to figure out, I want you to reverse the condition. So we're going to use a tree diagram, kind of like we did on that last problem. So to start out the tree diagram, we're going to first break it up by what I know. I can't break it up by whether you test positive or not, because I don't know what percentage of people test positive. I know what percent of people have HIV. So this is have HIV, and this is not have HIV. I know only 1% have HIV, and 99% do not have HIV. Okay, now given you have HIV, you could either test positive or you can test negative. Given you don't have HIV, you could still test positive or negative. So, which ones are which here? This is you have HIV. So if you test negative, that's a 3% chance, meaning there's a 97% chance you test positive, because you should test positive because you do have HIV. So this is 0.01 times 0.97. This is 0.01 times 0.03. And then the probability that you test positive if you don't have HIV, that's the mistake. And then this is a 94% correct decision. 9906 9994. All right, so I'm going to actually calculate these to make them a little bit easier. I think I can do this one in my head here. Is that move the decimal over 2? So that's 0097. This is 0.0003. This is, I can't do it. Was that 9906? 9906. 9906. 0.99 times 0.06. 0594. 0.0594. And this is going to be by far the biggest number here. 99 times 0.94. 9306. Okay? All right, so let's go back to what we want to find. I want to know the probability you have HIV given you test positive. That is, we're using the formula. This is on your formula sheet. Probability you have HIV and you test positive divided by the probability you test positive. So where is HIV and testing positive? So that's HIV and you test positive. That's this percentage right here. That is 0.0097 divided by the probability that you test positive. Well, these people test positive and these people test positive for different reasons. Here, you actually have HIV. Here, it's a mistake. So that's 0.0097 plus 0.0594. And that's my probability. 0097, 0594. So this is 0.0, dang it, 0097, 0.0097, 0.0097 plus 0.0594. There's no way I got that right. 05 now. Oh, yeah, me. Enter. 14%. 14.0. That's it. So if you test positive, you're probably going to freak out and think you have HIV, and you probably are going to think there's a really good chance I have HIV because I just tested positive, but really there's only a 14% chance that you actually have HIV. And you guys might be wondering, well, how is that possible? I mean, if there's the false negative is only 3% and the false positive is 6%. And you can kind of see it in these numbers here. Basically, it's because so few people actually have HIV. So 93% of people are going to not have HIV and test negative. But because such a large proportion of people have HIV, and this is 6%, 6% of the people that, I'm getting confusing myself here now. Let's look at it this way. Because so few people have HIV, the ones that test positive, but there's a very high chance that you test positive if you have it, that becomes little less than 1%. But because so many people test positive for HIV, there's a pretty good, because there's more people, there's a pretty good chance that if you test positive, you were probably going to be in this group, and thankfully not in that group. Okay? Suppose 1,000 people from this population were selected for HIV testing. How many would you expect to have HIV and test positive? HIV, test positive. That would be 97 people. Wait, 9.7 people. How many do you expect to have HIV and test negative? 0.3 people. I should have said 10,000 people. That would have been, well, whatever. Not have HIV and test negative. Not HIV and test negative. That would be 930.6 people. and not have HIV and test positive. That would be 59.4 people. And I think this is the reason I asked these is to try to illustrate this to you. You know, if you test positive, which group do you think you're probably more likely to be a part of? You're probably more likely to be part of this group, which is thankfully you don't have HIV, but tested positive anyway because of that false positive rate.